Johnny here with Simpson Math, and in this video we're going to be talking about the inverse trig functions. Now before I begin, remind me, what is a function? Function is, I plug in something and then the function spits out something unique. And there's even a vertical line test that comes with functions. So if I plug in an x value, it spits out a y, then that one point means I passed the vertical line test. If I plug in an x value and it spits out two y's, then it fails the vertical line test and is not a function. So a function is all about input, output. What is an inverse function? Yes. There's lots of possible answers here, lots of ways to talk about inverse functions. My favorite is the fact that inputs and outputs are interchanged in an inverse function. So if you think of a function as a machine, like normally I might give a machine $1 as input, and the machine would output a Dr. Pepper. So I'm Dr. Pepper machine. Put in $1, it spits out a Dr. Pepper. The inverse function of that, the inverse function, would interchange that. I would take a Dr. Pepper, put it into the machine, and the machine would output $1. So it's all about swapping the inputs and outputs. A lot of students remember from college algebra graphing a function and then on the same Cartesian plane graphing the inverse function. So they remember that fact, and so they remember there's this symmetry involved with the graphs. So one possible answer may be it's a reflection about that parent linear function y equals x. Because the x's and y's have been interchanged, inputs and outputs have been interchanged, there's this nice symmetric feel to the graph. So you may remember that. Along with that, the domain and the range have been swapped. Now the true definition of an inverse function has to deal with that composite definition. So if you take two functions and do their composition, and in the end you get out x, and you're able to do it both ways. So notice I have f composed of f inverse, and then f inverse composed of f. If they both simplify to a 1x, then by definition they are inverse functions. All right. So hopefully you remember all that from college algebra. Today we're going to be using that for the trig functions. Now, another way to talk about inverse functions is if a function is one-to-one, we know it has an inverse. One-to-one, it's kind of back to that. I plug in one input, it spits out one output. If it's the other way around, if every output only has one input, we call that function one-to-one. Any one-to-one function has an inverse. Now there's a quick little test to determine if a function is one-to-one, and that is the horizontal line test. All right, so it's another way you could have defined an inverse function is if the function is one-to-one, then it's going to have an inverse. All right, so we're dealing with the trig functions, and I can just envision sine right now, and I can already tell that there's something wrong with sine. If I just get a quick little sketch of sine here, I know sine of 0, 0, it starts the origin, goes up to 1, crosses, comes down to -1, and it just does this forever and ever and ever. And I could even go in the other direction where the maximum value is 1 and the minimum value is -1. And yes, this is a function. It does pass a vertical line test. But as soon as I try to do a horizontal line test, we've got a problem. In fact, this blue line right here, I already see 1, 2, 3, 4. There's going to be an infinite number of points there. So this is not one-to-one. Okay, that's okay. I'm going to move over to Desmos to help me with the graphing. I'm going to plug in sine again real quick. So there's the sine function I just graphed. And I can tell it's not one-to-one. But let's look at just a piece of the sine function. You probably did this in college algebra with the quadratic x squared. Oh, there's a big thing on my face. Hopefully that helps. So you may have done this with a quadratic where the quadratic, the parabolas, they too are not one-to-one. But we found the inverse function for x squared. It was the square root of x. The way we did that was we restricted its domain. I think we can do that something similar with sine. Let's take a look at sine over the interval. I'm going to cut it off at that low point here, this dot right here. This is the low point. If I go left of this point, there's this clearly like it's horizontal line failure. So I'm going to start there. Negative pi halves is less than or equal to x. And then I seem to be good up until this point right here at the pi halves. If I go any beyond pi halves, I'm going back down, and so I'm going to start to fail the horizontal line test again. So I'm going to stop myself just at pi halves. Okay, so we have a portion of sine, and this portion of sine is still defined as a function, and it even passes the horizontal line test. So what we're going to do to talk about the inverse sine function is we're going to restrict the domain of the regular sine. Now we have to do something similar to cosine and tangent, and I've written the restrictions above me. Sine, you're looking at it right here. We're restricting the domain to negative pi halves up to positive pi halves. I'll write that down, or you have it right above you. Let's look at cosine real quick. Same problem, right? This time, though, I'm going to restrict it to 0 to pi. So we see the similar situation. I'm at the high point at 0, so I'm starting there at the high point, and then I'm good all the way down to pi. But if I go just beyond pi, I'll start to come back up, and I will fail a horizontal line test. So we restrict cosine from 0 to pi. Let's take a look at tangent real quick. Lots of problems here. I'm going to fail the horizontal line test. Now, I think here I'll go from negative pi halves to pi halves again, but there's a problem at negative pi halves. I could include it in my domain for sine because it's an actual point, but tangent has problems at pi halves and at negative pi halves. So you notice I put a parentheses around the domain. I'll do that similarly here. I'm going to say negative pi halves is just simply less than x, which is less than pi halves. This portion of tangent, which is real nice because it not only shows a full period, but it also is one-to-one along this interval. So tangent seems really nice here. Okay, with those restrictions, we can talk about the inverse trig functions. Inverse sine, inverse cosine, and inverse tangent. Let me go back to my paper. I'll just kind of write down my notes, what we just did, just for fun. we look at sine over the interval negative pi halves to positive pi halves. If we do that, nice and curvaceous, something like this, then that slice, that piece of sine, we can do the swap. We can interchange the inputs and outputs. We say sine is 1-to-1 over this interval. So sine does have an inverse function. We call it inverse sine. There's another name, arc sine. Both of them mean the same thing. Two ways to write arc sine or inverse sine. One is this inverse notation. You should remember from college algebra. You would have an f of x and an f inverse of x. It's this weird -1 superscript. It's not the power of -1. It's just a superscript, -1 up there. That's inverse sine. I prefer arc sine. There's no debate here. Everyone knows what arc sine is. This first one, I'm not a fan of it just because a lot of students get it confused with the -1 exponent, which we just spent 6 weeks or all these videos working on calling the reciprocal of sine cosecant, like not calling that the inverse. So this is not cosecant. Let me write that down. Sine, if I take sine and raise it to a -1 power, let's say -1 power, that is the reciprocal of sine, which is cosecant. That's not the same thing. This -1 is not the same thing as that -1. Sine with a superscript -1 there is the inverse function. These are not the same thing. So if I ask you for sine to a -1 power, I'm asking you to reciprocate that value, or I'm asking you for the cosecant value. Here we're talking about sine inverse of x. This is completely different. Instead of reciprocating, we're now talking about inputs and outputs are being changed completely. It has that kind of swap feel to it, but arc sine and inverse sine is you're interchanging inputs and outputs. Reciprocal of sine is you just take your output and you put it under a 1, or you reciprocate it. All right. But using this information, I think I'm going to graph arc sine. I think I'll use Desmos to check myself, but I have these values, super restricted values from sine. I'm going to take those values and interchange them to get the values of arc sine. What I mean by that. I'm going to leave this up on here for a little bit longer, but I don't think I need this much longer. Normal sine of x. I'm going to get the pretty points on this super restricted version. So maybe like a little xy table. This point is when you plug in negative pi halves, sine is -1. There's another pretty point at negative pi 6, where sine is -1/2. Sine of 0, 0. Sine of pi 6 is +1/2. and sine of pi halves is 1. Now there's some more values in there. Pi thirds is root 3 over 2, but I'm just picking those pretty points. Sine inverse. Arc sine of X. If I want to graph the inverse function, one way to get those points is to simply take my inputs and outputs, or my x's and my y's, and interchange them. So instead of negative pi halves mapping to negative 1, sine inverse will map negative 1 to negative pi halves. I'm just interchanging these values. If I plug in 1/2 into sine inverse, it will spit out pi 6. This is that Dr. Pepper machine going in reverse. Now I have here some inputs and outputs, some x and y values, so I think I can graph sine inverse. Now, we just spent several lectures graphing the trig functions, and one big hurdle for a lot of us was labeling the x-axis correctly, because we had to do that whole skip dash dash dash. It's those radians along the unit circle. Well, that's all been thrown in the air now, because those axes, the x and the y axis, have been swapped. Now all of a sudden, my y-axis is the radian axis, and my x-axis is back to quote-unquote normal, I guess. So from 0 on my y's, I need the radians. So now I'm going to do up and down, skip, dash, 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 skip, dash. There's pi halves. There's pi 6. Similarly, skip, dash, 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 skip, dash. There's negative pi halves and negative pi 6. I'll choose where to put 1/2 and 1. And then I can plot the points that I just had. Negative 1 maps to negative pi halves. Negative 1/2 maps to negative pi 6. The origin, the zeros were interchanged, but it's still 0, 0. 1/2 goes to pi 6, and 1 goes to pi halves. Now this looks a little bit different. I mean, it's very similar. It has this curve up to 0 and a curve out, but it's slightly different. I want that to be more curvaceous. You know what? I should be using graph paper. I think I'm about to graph arccosine and arctangent, I will bust out graph paper to make this more curvaceous. But there is a graph of arc sine of X, or inverse sine of X. We simply took the inputs and the outputs and interchanged them. Arc sine. In your homework, I have you graph arc sine. This is what I want. I want you to, on paper, do your x and y axis, but now the y-axis has become the radian axis, so be very careful. And then get these points from what you're familiar with. So sine, we restricted it to this interval, negative pi halves to pi halves. Get some good points. Interchange, graph. Let's do that again with cosine. Let me grab graph paper. All right, I want to graph arccosine, or inverse cosine. The way to do this is, first I need to know how we restricted cosine. So cosine was different. It wasn't negative pi halves to pi halves. It's now 0 to pi. So I think what I'll do is I'll just get a list of good points from cosine along that interval. Starting at 0, cosine is 1, or cosine of 0 is 1. I know cosine is pretty at the thirds. If I plug in pi thirds into cosine, it spits out a 1/2. If I plug in pi halves, I'm now down to 0. 2 pi thirds is negative 1/2. And when I get to pi, I'm down to negative 1. And I can't go any further. If I were to go to 4 pi thirds, I'd be back up at negative 1/2, and I would fail a horizontal line test. So I'm super restricted. Arc cosine, or cosine, we restrict from 0 to pi. Now if I want to graph the inverse function, I simply take the x and y's, or the inputs and outputs, and interchange them. So instead of 0 mapping to 1, 1 will map to 0. I've got points. I think I can give a good sketch of this thing. Notice my x values, positives and negatives. My y values start at 0 and only go up. So I don't need anything below the x-axis. I only have non-negative y values. So I can put my y-axis, or my x-axis kind of low. But I do have positive and negative x values. So I'm going to put the y-axis in the middle. And if I'm going to pi, I need 12 squares if I'm using my let every square be 1 pi 12th technique. So I skip, dash, 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 skip, dash, 6 squares should get me to pi halves. Skip, dash, 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 skip, dash gets me to pi. I'll go ahead and label the thirds because those are so pretty. I'll let 2 squares be 1/2, 4 squares being 1. So I've labeled my axes accordingly with the data I've got. I'm just going to plug in some points. 1 is 0. 1/2 is pi thirds. 0 is pi halves. Negative 1/2 is 2 pi thirds. And negative 1 is pi. It should have a similar curve to it, where the sine wave and cosine wave were waves. The inverse sine and inverse cosine are almost like you see the DNA strands vertically. That's kind of what I picture. And if I were to continue, if I were to plug in 4 pi thirds, this curve would come back toward the y-axis. And that is a big problem because that would no longer even be a function. So I cannot go, back this direction. I cannot go back towards the y-axis. I cannot go back towards the y-axis. If I were to, though, continue this graph, it would kind of look like half of a DNA strand or something. All right, there is a picture of arccosine. Let's tackle tangent. Tangent is that cubic feel over and over again, so we restrict it to negative pi halves to positive pi halves. Nice. Okay, I'm going to get some good points in there. I'll go ahead and talk about those negatives. Negative pi halves is undefined or an asymptote on regular tangent. Sine is pretty at the sixes, cosine is pretty at the thirds, tangent is pretty at the fourths. Tangent of negative pi fourths is -1. Tangent of 0 is 0. Tangent of pi fourths is 1. If I went out to pi halves, it would be undefined again, a vertical asymptote. Arctangent, or inverse tangent, well, I'll just take those values and interchange them. So I'm now, something's weird going on at negative pi halves at the output. But -1 will map to negative pi fourths. 0, 0 becomes 0, 0. 1 maps to pi fourths. And then I've got this weird thing going on at pi halves. Okay, so x-wise, I have positives and negatives, so I need to put my y-axis in the middle. Y-wise, I have positive and negative values, so I need to put my x-axis in the middle. Now I need to go up to at least pi fourths, but I think I'm going to go up to pi halves. So I'm going to go skip, dash, 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 skip, dash. Because we restrict it to pi halves with a parentheses. So we go up to pi halves, we just can't include pi halves. Similarly down below, skip, dash, 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 skip, dash. This is negative pi halves. I'm going to label the fourths because they are so pretty. I'll let 2 squares be a half, making 4 squares 1. I'm going to plot, I only have 3 real points here, but I can plot them. -1 maps to negative pi fourths, 0, 0, and 1 pi fourths. Now to help me graph this, I'm going to think about what happens on tangent, regular tangent, at the pi halves. So normally it's a vertical asymptote and I'm approaching it, but I never quite touch it. So that same thing is going to be happening here, but that asymptote has been changed to a horizontal asymptote. I will still approach pi halves, I just won't touch it. I'll still approach negative pi halves, I just won't touch it. And I know how asymptotes help me with graphs. The graph tries to become the asymptote. So as I move out to the right, I'm going to curve up, but then very quickly approach that asymptote and try and become it. It doesn't flatten out, but it looks like it does because it gets so close so fast. Similarly, as I move into the negative region, I'll kind of curve down, come into this point. I should have made this a bit more curvier. Curves into it, and it flattens out as fast as it can. So there I have arctangent. I only have 3 points, but there's this nice curve, and then the asymptotes help me guide the rest of the graph. All right. So now we have pictures of the inverse functions. Practice graphing those a few times. They're in the homework. Be nice and neat. Get those down. Especially the restrictions. Get those memorized or embedded in your brain. Now, moving on, let's see what we can do with these inverse functions. Inputs, outputs, interchanged. How does that help us? Well, let's go back to our triangle problems that we've been solving. I'll call this side 4, this side beta. I'll call the hypotenuse x. We've been using trig to find the ratios. When you input angles, you output the ratios of the side lengths of a triangle. Let me just kind of write that down. With inverse trig, it's the reverse. I can input the side lengths of a triangle, and the inverse functions will spit out the angle. So all along I've been saying, what is cosine of pi thirds? And you would tell me, oh, well, the output's 1/2. Now it's kind of reverse. Arccosine of 1/2 will spit out the angle pi thirds. So I have this right triangle. I know one side length is 4. I know that angle up there is beta. And I know the hypotenuse is x. And I want to find beta. We've done similar triangles where I've asked you to find x. Well, this time I'm trying to find out the angle. But we do the problem very similarly. We set up a trig equation that relates 4, beta, and x. A regular trig equation that relates those three. So hopefully you can tell that adjacent to beta is 4, and the hypotenuse is x. So the SOHCAHTOA definition helps here. Cosine of beta is adjacent over hypotenuse. So I'm going to write that down. Cosine of beta is defined as 4 over x. But this time I want the beta. I don't want the x. I'm not solving for x this time. I'm solving for beta. Now what makes this extremely difficult is beta is the argument of the cosine function. This is not the letter cos being multiplied by beta. I cannot divide by cos. That makes no sense whatsoever. Cosine beta is one thing together. It is a function with its input. But if only I had a tool that would take the input and the output and interchange them. Oh yes, inverse functions do that. So I can solve for beta. Beta will be equal to arccosine of this 4 over x. Notice the beta and the 4 over x have just changed positions. In fact, a better way to write this would be cosine inverse of. So I'm changing cosine to cosine inverse. I'm interchanging my beta and 4 over x. So the 4 over x is now inside, and the 4 over x has become beta. Those say the same thing, but maybe this one helps you visualize that the inputs and outputs have just been interchanged. And we're done. We have solved for beta. Beta is all by itself. Beta will be arccosine of 4 over x. Whatever that is, that'll be it. Let's just do that again. Here I have a right triangle with hypotenuse 7. This side length is 3. And this angle is alpha. And I want to find alpha. What is it? All right, well, this time I'm given alpha, so I was given an opposite and the hypotenuse. So I'm thinking sine. Sine alpha equals 3/7. I want alpha by itself. Well, I can take alpha and 3/7 and interchange them if I use my arcsine or inverse sine notation. Sine inverse of 3/7 is alpha. I have found alpha. It's by itself. I'm done. Now that value I can actually plug into a calculator if I needed to. I guess that might be okay to do. So your calculator will have a sine inverse button. Mine's right on top of the sine. Now again, this is not cosecant. This is not the reciprocal of sine. This is inverse sine. So I'm going to hit inverse sine. I'm in radian mode right now, so whatever angle it gives me will be in radians. In fact, let me switch out of that. I'm talking about a triangle, so I'd like to see what like degrees that is. To me, this is just a sketch, but it looks like 35 degrees or something. Let me try it again. Okay, I'm going to switch my mode to degree. Arcsine 3 divided by 7, close my parentheses, and I get 25-ish degrees. So the exact value is arcsine 3/7. That's a true equal sign. If you're needing an approximation, then you can use technology, but if you're going to have to round, I'm sure. So use a little double tilde or a wavy equal sign to say, this is not exact, I'm just approximating. The calculator is getting as close as it can. All right. Now, we can do some fun problems like this. I want to find the exact value of arcsine of the square root of 3/2. All right. So normally I would ask you, what is sine of pi 6, an angle? And you would tell me, oh, that's 1/2. Well, this time it's reverse. I'm giving you the ratio. That root 3/2 should look very familiar to you. And this is asking, well, what angle would give me that root 3/2? As soon as you see the word arc or inverse, think of the restriction. So this is asking what angle input of sine over that very restricted negative pi halves to pi halves would give me root 3/2. I'm going to bust out a unit circle to help me visualize this. I'm looking for a sine value of root 3/2. Well, I see one at pi thirds, but I also see one at 2 pi thirds. Both of these have a output or a y value of root 3/2. Oh, but we restrict sine. We're not talking about these values over here. Arc sine is restricted from a negative pi halves up to a positive pi halves. So even these values are not quite right. This is a negative pi 6, negative pi fourths, negative pi thirds, and a negative pi halves. So from negative pi halves up to pi halves, is there a y value that is positive root 3 over 2? Yes, it happens at pi thirds. Sine of pi thirds equals root 3 over 2, so arcsine of root 3 over 2 should equal pi thirds, assuming we're in that interval. Let's do it again. What is arccosine of that same value, root 3 over 2? So what angle input of cosine over its restriction 0 to pi outputs root 3 over 2? Well, cosine is pretty, a half at a third, so this must be the pi 6. Cosine is root 3 over 2 at pi 6, and that is in the interval 0 to pi, a different interval. Arccosine is now looking from 0 up to pi. But that's nice and pretty at pi 6. All right, same question. Arcsine of negative 1/2. What angle would I have to put in sine over the interval negative pi halves to pi halves would spit out a negative 1/2? Well, I have my unit circle. I'm not talking about those two quadrants. I see a sine value of negative 1/2 sitting right here. So what's the angle? If you said 11 pi 6, you're wrong. Let's try that again. Arcsine is restricted to negative pi halves to positive pi halves. I'm looking for the angle that will spit out a negative 1/2. I agree, we're looking at this value right here. But if you answered 11 pi 6, in order to get to 11 pi 6, I have to start here at 0 and go in a positive direction up to 90 degrees and then go into this restricted area. No. I cannot even get to 11 pi 6. It's too big. It's outside of that interval. So instead, I have to start at 0 and go negatively down to negative pi 6. Negative pi 6 is in my restriction. Let's try that again, if that was confusing. I got another one for you. What is arctangent of negative 1? Where do we restrict tangent? Same as sine. Quadrant 1, and we can probably think of this as quadrant negative 1. These need to be negative values, because I'm going from negative pi halves up to pi halves. Where is tangent going to be negative 1? Well, it's going to be down here at this position. What angle is that, though? Negative pi fourths. 7 pi fourths is not in my restriction. All right, so these are just the unit circle questions in reverse. So those same inverse, or the same questions I could ask you about the unit circle, I can now ask you in reverse. Fun times. Let's take a look at this scenario. Cosine of cosine inverse of 1/5. Okay, well, I think we just talked about this arccosine stuff, but 1/5 is not on the unit circle. So this inside the parentheses, the big ones, this is an inverse cosine question. It's giving me a ratio of side lengths of a right triangle, and it's asking for the angle, just like the above questions. I was giving you these side lengths, which come from a right triangle, the sides of a right triangle, and I was wanting the angle that did that. So 1/5 is not on the unit circle. It's not going to be a nice pretty angle. But this is asking, what is that angle? Okay, I'm going to draw a triangle in such a way that cosine of the angle would be 1/5. Let's see if you can follow this. Someone mentions trig, they're talking about right triangles. This is referring to some angle in a triangle. I'm going to call it this one down here, and I'm going to call it theta, because that's what I'm used to. Well, cosine is defined as the adjacent over the hypotenuse. I have a fraction here, 1/5. I'm going to label my adjacent 1 and my hypotenuse 5. I think then that cosine of theta equals 1/5. If I inverse that, arccosine of 1/5 would equal theta. Input, output, interchange. So this inner arccosine stuff is describing this triangle situation in which it's asking for that theta. This inside here is just theta. I don't know the angle. 32 degrees, I'm not sure. But it's that angle theta. Now my question is, well, what is cosine of theta, of that angle? Oh, I know what cosine of that angle is. Cosine of theta is 1/5. Oh, yeah, okay. This should make some sense. Cosine and arccosine are just inverse like operations. They undo each other. So if I said, what is 2 cubed? Oh, and by the way, I then want you to cube root it. Well, 2 cubed is 8, and the cube root of 8 is 2. You just get back what you started with. That makes sense. So cosine of arccosine of 1/5 should give me that 1/5. Yeah, should. All right. I'm going to come back to this, though. So I'll hang on to that. Let's try something similar. Arccosine of cosine of 5 pi thirds. Let's think about what it's asking. Inside the parentheses is an old question. What is cosine 5 pi thirds? That's going to spit out some ratio side length. And then I'm asking for arccosine of that side length. So now I'm asking for the angle that will give me that. So my final answer should be some angle. Okay. There's a problem, though, with arccosine, and what is it? It's restriction. I can only talk about cosine from 0 to pi. 0 up to 5. Pi. 5 pi thirds, yep, is way over here. I can't talk about that. That's not in my domain. To talk about cosine, I have to go from 0 to pi. I can't even go in the negative region for pi. I can't talk about that. I don't know what to do. Okay, well, let's zoom in on just these parentheses. I think I can answer this question. What is cosine of 5 pi thirds? So I'm not dealing with the arcness yet, the inverse stuff yet. I just want to know, what is cosine of 5 pi thirds? Cosine and 3's go well together, so it's going to be a half. Is it positive or negative? Well, it's it's right of the y-axis, so it should be a positive 1/2. So I simplified that trig question first. Now I've got a new question. What angle spits out 1/2 dealing with cosine on that interval? Well, that looks like pi thirds to me. All right, so the inverse and the regular functions, they don't always just undo each other. If you think about a square root function, if I take -2 and square it, that is -2 times itself, what would I get? Positive 4? Well, let me undo that. Let me take the square root of that 4. Well, all of a sudden I got a problem. The square root of 4 is 2. I mean, yeah, technically it's also -2. But you see there's a problem. I started with -2, but if I take -2 and square it, I get 4. The square root of 4 is 2, not what I started with, -2. And that's because there's a domain restriction with the square roots as well. Parabolas are not one-to-one functions. We have to restrict their domain from 0 to pi, and then the inverse of that is the square root function, which looks like this. But it's only defined from 0 to infinity. There is no negative talk. So this undoing doesn't always quite work. That's similar to what happened over here. 5 pi thirds, I can't talk about it. But I could simplify it to 1/2, and then, okay, well, pi thirds does that. Okay, so these inverse functions, it's all about the domain, it's all about this restriction. So every time you see that inverse notation or the arc notation, think to yourself, what's the restriction? Next problem. Let's do sine of arccosine of 3/4. Regular sine has no problems. Arccosine, I'm restricted from 0 to pi. Cool. Okay, now these are completely different functions. The arccosine and cosine, the arccosine and cosine, those have been kind of like undoing each other, but sine and arccosine are completely different. Okay, well, let's think about what's going on here. Inside my parentheses, we have an arc question. This is talking about an angle. It's asking for the angle. Once I get the angle, I want to know, well, what is the sine of that angle? I think I'm gonna have to go back to my right triangle and just figure out what's going on here. As soon as you mention sine or cosine, you're talking about a right triangle. I'll label it the same, theta down here, right triangle. This is very similar. Cosine of that angle will give me 3/4. That is the adjacent over the hypotenuse. So the 3 must be here, and the 4 must be there. This triangle says cosine theta is 3/4, or arc cosine of 3/4 is theta. So I'm saying what's inside these parentheses is this angle right here. I don't know what it measures. I don't care. It's just going to be theta. This whole thing is going to be one big giant theta. Well, then the question is, what is sine of that angle theta? Well, sine of an angle would be the opposite side length over the hypotenuse. Well, I can do this. Pythag can help me find this other side length. I'll call it y. 16 minus 9 is 7. So y is the square root of 7. So then I can answer this question. Sine of the angle that this describes would be root 7 over 4. All right. That was fun. Let's do, that was tricky, but let's do another tricky one. Sine inverse of E. Okay, well, I see a sine inverse, so I know I'm restricted from negative pi halves to pi halves. It's an inverse question, so I know it's asking for an angle between negative pi halves and positive pi halves. What is E? E is representing here a ratio of side lengths of a right triangle. And we know E is Euler's number 2.7 blah blah blah. It's an irrational number, kind of like root 7 or kind of like pi. It's just a decimal that goes on forever, 2.7 blah blah blah. What angle could I put into sine that would spit out 2.7 something? Input, output. All right, to help me explain this, let me redraw a sine real quick. Sine's graph looks something like this. What is the highest number sine ever touches? 1. The lowest number, -1. So this is asking, what angle of sine spits out a number that's really close to 2.7? Well, if you told me a half, I would tell you pi 6. If you told me root 3 over 2, I would tell you pi thirds. If you told me pi halves, I would tell you 1. I'm not going to get anywhere close to 2. Sine never comes way up here. If this is 2, 2.7 is up here. There's no way. I'm never going to do that. That's never going to happen. This is not defined. This is just never going to happen. Never. You may see a couple of these types of questions in your homework. Just making sure you understand what's going on here. That this is now, it was the output. So sine is only ever going to get as low as -1 and as high as +1. If I ask you for something bigger than 1, it's not going to happen. Previously, 3/4, that's okay. I asked you for arccosine of 3/4. Well, this is 0.75. That is less than 1. 1/2. Oh, that's fine. 1/5. These numbers are all fine because that's less than 1 and not less than -1. So those numbers are fine. But anything bigger than 1 is that's not going to happen. So yeah. Okay, now I just have additional practice. In fact, let me just put this here. Pause the video and try these, and then I'll just kind of work them. Alright, so there were some just examples for you to play with. If you'd like some more, just ask me and tackle the homework, and I'll see you in the next video.